Hey everyone, Professor Adjuvant here to talk to you about what limits are and how to find them graphically. Okay, so a limit, abbreviated as LIM, that's the notation that we use for when we're solving limits, is in simplest terms what it looks like the graph is going to be as we approach a specific x value. Okay, so the limit as x approaches some value, let's say a. Right, we're approaching this a value that's marked here on the x-axis, and this is the notation, right? Under LIM, we write x approaching a. So what does it look like we're going to be on the graph as we're approaching this? So the way that I always tell my students is to put their pencils or their fingers on the graph on both ends and then move them slowly following the graph closer and closer to the A point and see where your fingers end up. Okay, so we would start down here on the left and we would follow the curve all the way along until we get to what it looks like A is going to be. Now the limit is not what the actual value is, it's what it looks like it's going to be. We would do the same thing going from the right. We would approach this value. Now if our fingers, if it looks like it's going to hit the same thing coming from the left and the right, in this case it looks like it's going to hit this B value, that is what the limit is. It's that simple. However, it's not always going to be like this. Right? There's a lot of different things that can happen, a lot of interesting things that can happen at specific points on a graph, and the limits will change depending on that specific point and what's happening. Not only can we find the limit as we approach a value, we can do what's called a one-sided limit, where we approach that value from just the left, or we approach that value from just the right. So this, the limit as x approaches a with the little negative sign, does not mean that we're now approaching some negative a value. It means that we're approaching a, but we're approaching it from the left-hand side only. Same thing with the positive sign. This means that we're approaching a from the right-hand side only. Okay, so both of these could be different values if there's something interesting going on here, and we'll see an example of that in just a second. Now, if these two are equal, right, the limit as x approaches a from the left is equal to the limit as x approaches a from the right, then it's equal to the limit as x approaches a from both sides. Okay, so in order for this limit to actually exist, we need both the left-sided limit and the right-sided limit to be the same value. Alright, not only can we look at the limits at a specific point, we can also analyze what is the actual functional value at that specific point. So this gets a lot easier to see with several examples. Alright, so we have this graph, right? And on the left, we're starting and we come up, and then suddenly we jump and we come down here. Right? So this would be like a jump in a piecewise function. Something's happening at -7 that changes us from this position up here, this open circle, down to this closed circle, and then we continue along. At this point 3 that we're going to analyze, we're nice and continuous, and we continue on, and then there's this weird hole in the graph, and we continue on after that. Alright, so let's analyze the limits, both one-sided and the complete limit, and the functional value at these three interesting points that I've highlighted, -7, 3, and 9. Alright, so how are we going to do this? Well, the limit as x approaches -7 from the left just means what does it look like the graph's going to hit when we approach -7 from the left-hand side. So as I'm approaching -7 from the left, we're getting closer and closer. We get infinitely close to -7 without actually touching it, and it looks like we're going to hit the value 1.5. Now we're not actually at that value because it's an open circle, but that's what it looks like we're going to hit, and that's what limits are all about. What about as we approach -7 from the right? Well, as we approach -7 from the right, we're on this other line, and it now looks like we're going to hit -4. All right, now in order for this limit to exist, the limit as we approach -7 from both sides, these two values need to be the same. Well, 1.5 and -4 clearly are not the same value, so what we would say in this situation is that this limit does not exist, DNE. Now, what about the actual functional value? What is the function actually at -7? Right? What is f of -7? Well, at -7, we have 2 points, kind of. We have one that is an open circle and one that is a closed circle. So if you remember how piecewise functions work, the open circle just means that we're getting infinitely close to -7, but we're not actually there. So at -7, we're actually down here at the closed circle point of -4. All right, so this, and we'll talk about this in another video, is called a jump discontinuity, where the graph literally jumps. All right, so that's one interesting thing that can happen when you're evaluating limits. What about 3? Well, as we approach 3 from the left, it looks like we're going to hit 1. Easy enough. And as we approach 3 from the right, it also looks like we're going to hit 1. So because these are the same values, the limit as x approaches 3 is also this number, 1. F of 3, the actual point of the graph at that value, in this case is also 1. Now when all of these are the same value, the left side limit, the right sided limit, the actual limit from both sides, and the function at that point, when all 4 of these things are the same values, this is continuous. That tells us that the graph is continuous at that point. Our third example for this graph, as we're approaching 9 from the left, what does it look like we're going to hit? Well, it looks like we're going to hit +4. As we approach 9 from the right, what does it look like we're going to hit? Well, it looks like we're going to hit again +4. Now, because the left-sided limit at 9 and the right-sided limit at 9 are the same value, they're both 4, then the limit as x approaches 9 is also that value of 4. However, what is the actual value when the function is 9? What is f of 9? Well, if we look at f of 9, there is an open circle on the line and a dot, a point, off on its own. And this point is the actual function value. So the function at 9 is 2. All right, so this is a hole. So we have a hole, we have a jump, and we have a nice continuous part of the graph. All right, so these are 3 of the 4 things that we could see when we are evaluating limits. The last thing that we can see when we're evaluating limits graphically is going to be an asymptote. All right, so we have this asymptote at 4. So what does it look like the graph is doing as we are approaching 4 from the left-hand side? Well, we're approaching this 4 value and the graph starts shooting up, right? That's the definition of an asymptote. We're approaching that value, we're getting closer and closer to it, but the graph is just going higher and higher and higher up to infinity. And that infinity that it's going up to is actually what this limit is equal to. Positive infinity. When we approach 4 from the right-hand side, we're coming down, and we approach the asymptote again, and we're going to get closer and closer to this 4 value, but the graph is now shooting down. It's going to go down forever and ever, getting closer and closer to negative infinity. which is what this limit is equal to. Now infinity and negative infinity are not the same thing, so this limit as x approaches 4 from both sides does not exist. And if I try to plug 4 into whatever this equation is, I'm going to have an error, right? Something is going to be happening because I am getting this vertical asymptote, which probably means I'm dividing by 0. So the f of 4 in this case, because it's a vertical asymptote, is going to be undefined. All right, and just like that, we've seen all 4 situations, a jump, a continuous, a hole, and an asymptote for finding limits graphically. If you found this video helpful, consider giving it a like and consider subscribing to the channel. Thanks for watching, good luck, and we'll see you in the next one.